Oh, the secret ingredient we're hunting for today is sulfur. It's absolutely essential for plant life. It's a key building block for proteins, for enzymes, you name it. Without enough of it, plants just can't grow properly. But, like any good recipe, the amount has to be just right. So the real question is, how in the world do you measure something you can't even see?
Okay, this is our magic number, 10 parts per million. According to all the soil science standards, this is pretty much the critical level for sulfur in the soil. If you've got less than this, you might have a problem on your hands. This number is our target. It's what this entire investigation is all about.
And that is exactly what we're going to do. We're going to follow the official standard operating procedure, the SOP, for testing available sulfur. You should think of it as our detective's manual, our step-by-step guide for uncovering the truth that's hidden in the soil. Every detective needs a toolkit, right? But for this case, forget about magnifying glasses and fingerprint dust. Ours is filled with some very specific chemical reagents. These are these specialized tools that are going to help us crack this case wide open.
First up in our kit is the extractor. This is a monocalcium phosphate solution. Its whole job is to go into that soil sample and act like a tiny magnet, pulling all the available sulfur out and holding it in a liquid solution for us. And precision here is everything. The SOP calls for a solution made by dissolving exactly 2.035 grams in 1 liter of water. No guesswork allowed.
Next, we've got the revealer, barium chloride crystals. Okay, now this is where the magic happens. When we add barium chloride to our liquid extract, it reacts with the sulfur to create something called barium sulfate. And because barium sulfate doesn't dissolve in water, it forms this cloudy haze. This is the key to the entire test. It's how we make the invisible sulfur suddenly visible. And finally, we need our stabilizer. This is a gum acacia solution. It stops all those tiny, cloudy barium sulfate particles from clumping up and sinking to the bottom. By keeping them floating evenly throughout the liquid, it makes sure that our final measurement is accurate and reliable. And it doesn't take much. We just need 1 milliliter of a 0.5% solution to get the job done. All right, with our toolkit ready to go, the investigation begins. The very first step is extraction. We've got to get that sulfur out of the soil sample and into a solution we can actually work with. So let's see how it's done. And the official procedure starts with a really simple but totally vital instruction. Shaking the sample packet makes sure everything is mixed up evenly. It means the small bit we test is truly representative of the whole batch. It's a tiny step that prevents some really big errors down the line. The process itself is super methodical. We start by weighing out exactly 20 grams of soil. To that, we add a half a gram of activated charcoal, which is in there to help keep the final liquid nice and clear, and 100 milliliters of our extractor solution. Then the whole mix goes onto a mechanical shaker for a full hour. No cutting corners. This makes sure we pull out as much sulfur as we possibly can. The final step is to filter it all, which leaves us with a clear liquid, and that's where our sulfur is hiding. So we've successfully extracted our evidence. Now comes the most exciting part of the whole investigation. The revelation. This is the moment we make our invisible sulfur finally appear. First, we take a small, super precise sample of our liquid. It's called an aliquot, and in this case, it's exactly 10 milliliters. To this, we add our revealer, 0.2 grams of barium chloride crystals. This is what sparks the reaction, creating that telltale cloudiness. We immediately add that 1 milliliter of gum acacia to stabilize the mix, and then we wait. The SOP says to wait for 60 minutes to let that cloudiness fully and consistently develop. This whole process has a name. It's called the turbidity method. And the principle behind it is just beautifully simple. The amount of cloudiness is directly related to the amount of sulfur in the sample. More sulfur means more of that cloudy precipitate, which means a cloudier solution. Simple as that. Now we just need a way to measure that cloudiness with precision. And for that, we bring in the high-tech gear. This is a spectrophotometer. Its job is to shine a perfect beam of light right through our cloudy sample. On the other side, a detector measures exactly how much of that light makes it through. It's what turns that visual cloudiness into cold, hard data. Okay, we have our reading from the spectrophotometer. Now it's time to interpret the results and deliver the final verdict on our soil sample. This slide really illustrates what the machine is doing perfectly. If there's very little sulfur, the sample isn't very cloudy, right? So lots of light gets through. That's high light transmission.
But if there's a ton of sulfur, the sample is super cloudy, and it blocks a lot of the light, which gives us a low transmission reading. It's a simple inverse relationship.
So how do we translate that light reading into an actual sulfur concentration? Well, we use something called a standard curve. Scientists create this by making samples with known amounts of sulfur, like 1, 3, and 5 micrograms per milliliter, and then measuring their light transmission. This creates a reference chart, like a cheat sheet. We just compare our sample's light reading to this chart, and it tells us the exact sulfur concentration. With that concentration number in hand, we plug it into one last formula. This final calculation takes into account the initial soil weight and all the liquid volumes we used, and it converts our reading into the final verdict, the parts per million of available sulfur. And just like that, we finally know if our soil is above or below that critical 10 ppm threshold. Case solved. So there we have it. We have our answer. The invisible has been measured. But this leads us to what might be the most important question of all. Knowing the number is really just the first step. For farmers, for agronomists, the real work starts now. What does this verdict actually mean for the field, for the next crop, and ultimately for the food that we all depend on?